Asterisk asterisk the siren's pitch drops even though it never changes. Asterisk asterisk higher note as ambulance rushes toward you. Lower one as it passes. Why does the same sound feel different? Motion rewrites what your ears hear. Picture an ambulance racing toward you. Its siren blares the same frequency it always does. As it approaches, the sound waves in front of it squeeze together. The compression makes each wave arrive more often at your ears. Your brain registers a higher pitch. When the vehicle passes and moves away, the waves pull apart. They stretch out, arriving less frequently. That stretching lowers the perceived frequency, so the siren sounds deeper. What you should remember. Pause 0.8 sound travels through the air in the form of pressure waves. These waves are created when air molecules vibrate and push on neighbors. The vibration causes alternating regions of compression and rarefaction. As each region moves, it carries energy without moving the air itself. The speed at which these pressure changes propagate is called the speed of sound. In dry air at 20 degrees C, that speed is about 343 meters per second. Temperature directly influences this speed because warmer molecules move faster. When temperature rises, the medium becomes more compressible and waves travel quicker. Conversely, colder air slows down the propagation of sound waves. Understanding these mechanics explains why sirens seem lower when a vehicle approaches. The Doppler effect is simply a change in frequency due to relative motion. But first we must grasp how sound itself moves through the atmosphere. Pause 0.8 when a siren moves toward you, its sound waves squeeze together ahead of the source. This compression shortens each wavelength, making the waves arrive more frequently at your ears. The emitted frequency stays constant, only the spacing between successive fronts changes. As the siren passes and begins to move away, the wavefronts stretch apart behind it. That stretching lengthens the wavelengths, so the waves reach you less often than they were emitted. The shift in arrival rate is what we call the Doppler effect, a direct result of relative motion. In the animation, you will see two siren icons, one moving toward the observer and one receding. Each icon emits identical wavefronts, but their spacing on the left side is tighter than on the right. The labels compressed and stretched help illustrate how the source's speed alters perceived pitch. By observing these changes, you can predict whether a siren will sound higher or lower as it passes. Pause 0.8 when a siren moves toward you, its waves compress and the frequency rises. The compressed waves arrive more often, so your ears register a higher pitch. As the siren passes the point of closest approach, the compression stops abruptly. Immediately after passing, the waves stretch out because the source is moving away. This stretching reduces the frequency, and the pitch drops noticeably for listeners. The change in frequency can be plotted on a timeline graph against distance from the source. In that graph, the approaching phase appears as a steep upward slope of color red. The receding phase shows a gentle downward slope colored blue to contrast the rise. The magnitude of the shift depends on the siren speed relative to sound speed in air. Understanding this mechanism explains why emergency vehicles seem louder before they pass, and softer after. Pause 0.8 The Doppler effect explains why a passing siren sounds lower as it approaches, and higher as it recedes. When the source moves toward you, sound waves compress, raising the frequency that reaches your ears. Conversely, when the source moves away, waves stretch, lowering the received frequency. A simple relation captures this. F equals F times V plus VR slash V plus Vs, where V is air speed and Vs, VR are source and receiver speeds. Human hearing is most sensitive between 2 kHz and 5 kHz, the range in which siren tones lie. Rapid pitch changes can exceed the ear's ability to track frequency shifts smoothly. In high-speed scenarios, the ear perceives a sudden drop rather than a gradual glide. This perceptual lag is partly due to neural processing delays of about 10 ms. Additionally, the auditory system prioritizes steady tones over fleeting transients. Therefore, a fast-moving siren may feel blunted in pitch even though physics predicts continuous shift. Understanding this mismatch helps engineers design clear emergency alerts for moving vehicles. Pause 0.8 when an ambulance approaches, its siren seems higher in pitch. This change is not because the siren changes tone. The source emits a constant frequency, The sound waves are unchanged. What shifts is how our ears receive those waves as the vehicle moves. If the ambulance comes toward you, the waves compress and arrive more often. This compression raises the perceived frequency, making the siren sound higher. When it recedes, the waves stretch apart, lowering the perceived pitch. The same principle explains why traffic noise feels louder when cars pass quickly. Here, the source speed is high relative to you, so sound pressure rises, but the actual vibration rate of each car's engine stays constant. Thus, all sirens and engines emit a fixed frequency. Motion only changes perception. Remember, Doppler effect is about relative motion, not changing source tones. Pause 0.8. We saw that motion changes perceived pitch, not the siren itself.